Well, that means hello in sign language. Aboriginal Marian. We are a team of four, and we're working on a sign language translation system, basically meant to bridge the communication gap between the society. So we have all been in a situation whereby you're trying to speak, but someone is not giving you a chance, or people are not getting what you're trying to put across, and you know how this makes you feel, or you're in a group of people, but there is social isolation. Okay, you're not connecting well with those people. You know how that makes you feel. It could actually cause a mental health issue. Now we are focusing on how the deaf individuals feel in our society. They want to communicate with us, but we can't understand what they're trying to put across. So at times they just tend to lay low and just isolate themselves. So in an attempt to bridge that communication gap, I introduced to you a real-time sign language translation model. It's going to work instantly, real time. It will translate those sign language gestures into text as well as voice or audio where need be. And this will bridge the communication gap, and it will make our society more inclusive, whereby both the hearing and those with hearing disabilities feel included in the society. And this will improve their social engagement, their mental health issues, and they'll feel included. So our project objectives, we have to develop a real-time system, since it's going to be translating the sign language gestures into text as well as audio. Then we have to employ advanced deep learning models like the CNN, VITs. Then we have to integrate a GPT model. It's contextualizing the translated text, then enhancing the accuracy. Then we have to elevate the system's performance. We are comparing at the already existing sign language translation models so that we see that our system works up to date as well. Then the solution overview, I'm going to be focusing on the innovative aspect of this solution. It uses CNNs for accurate gesture recognition. We found that out during our training process of our models. Then it enhances performance with the other models like the CAPSNets, VITs, DQNs to improve the gesture recognition. Then it achieves high accuracy. So it's when you translate a video, it gives you the correct response. Then we have overcomes data limits via argumentation. Then this image, it gives you a rather detailed structure of how our system works. It incorporates the aspect of deep Q learning, the natural language processing, then the computer vision, where you're going to input in your video. It will be processed using the CNNs, the CAPSNet, just as I've said. Then it will be able to translate and give you an output either in text or audio. Then the data we used a Uganda sign language data set. It's basically a video-based data set. It captures the hand gestures properly. They are short videos, so that we can focus on the hand movements and body postures. Then before using that data set, we carried out the cleaning to make sure that everything is well before we can proceed to the next stages. So in the cleaning process, we have filtered incomplete videos, standardized the frame rates, then verified the data labels to make sure they're accurate. Then we proceeded to pre-processing, where we extracted frames and normalized the pixel intensities, then stored the hand keys, augmented data, then split the data into train, validation, test sets, so that we can get to know our data set more. Thank you.
Models and techniques. We created the CNN models, which is based for spatial feature extraction, and our CNN model had an accuracy of 93%, and it was the best. Then we also used the random forest, the SVM, and the KNN, which is benchmarked for static gesture classification, but it's limited to sequential tasks or sequential capturing. Then we move on to the long short term memory. We also use long short term memories when we're creating our models, which is best for capturing temporal dynamics, or it's best for sequential hand movements. Then we also created a vision transformer model, which handles long range dependencies in video frames, and it's better than the CNNs. And our vision transformer achieved an accuracy of 89%. Then we also had the capsule networks, which preserve special hierarchies of the gestures. Moving on, that's it for our models. Moving on to our systems architecture. We have the front end, the back end, the fine-tuned CNN model, and the model inference. And at the beginning, when the front end captures or uploads a video, the frames are sent to the back end for processing, normalization, capturing or feature extraction, capturing of key points. Then the processed frames are passed through a CNN or a fine-tuned CNN model, our model. And then the CNN model will extract its features and passes them to the model inference. And when the model inference generates its predictions, the predictions are sent back to the front end. Moving on to our implementation details, in our model training, the libraries that we used was TensorFlow, and the platforms that we used was Google Colab and Kaggle. In the back-end model inference API, the framework that we used was Flask, and the libraries was TensorFlow Lite Interpreter, NumPy, and Pillow. Then front-end, our UI, we created it using Streamlit, and deployment, we deployed on Render and used Hugging Face when we were uploading our model. Then for monitoring, we used Grafana. Next, we have the results and evaluation for our different models. The first table shows the different accuracies, precision, recall, F1 score, and this was what we used to measure our model's accuracy. Yes, and to measure our model's accuracy. And the different graphs that we have the training loss graph, which was for our MLP model. Then we have the confusion matrix next, which was for our DQN. Then the other confusion matrix was also for our MLP model. Then the one above was for our CNN model. Thank you.
Hello everyone, my name is Atwele Brian and I'm going to continue from where my colleague stopped. I'll take you through impact and relevance. In the Ugandan context, we know about 5 million people in Uganda. They suffer speech impairments. That means it's about 10% of the Ugandan population out there that suffers because of communication barriers. Our written translation will break those barriers faced by the Ugandans in sectors of education, healthcare, and employment. Our target beneficiaries include educators, the deaf, the employers and entrepreneurs, healthcare providers, NGOs, and then governments. Still under impact and relevance, we have what we call the SDG. SDGs are simply sustainable development goals that were set by the United Nations, and these are 17 global goals aimed at making the world a better place by the year 2030. Our project aligns with 5 of them, which means you're on the right path to make the world a better place. We align with quality education, reducing inequalities, good health, and well-being. We have a decent work and economic growth in partnership for the goals. Moving on to intellectual property and innovation, our project is protectable, and this is simply because we have potential intellectual assets that are copyrightable, that are patentable, that fall under trade secrets and all that. Our potential intellectual assets include the algorithms, processes, data, and the software UI. Our protection strategy, we have different, of course, the patentable, we have a novel AI model and the real-time gesture recognition process. Yeah, this is patentable because, yeah, it's ours. Then the copyrightable, we have the key point data set, software code, and then the UI UX design. We have the trade secrets, which are the pre-processing techniques that no one can ever know except us. Yes, and moving on to monetization and scaling, subscription-based APIs, the business to customer mobile app, hardware integration, government, and NGO partnerships, advertising. Generally, we shall introduce ads that pop up on the free versions, and then all the other monetary ways. According to the Ministry of Health, like we had seen, 10% of Ugandans are speech impaired. That means we have a large potential market. And yes, moving on to the SWOT analysis, we have strengths, weaknesses, threats, and opportunities, just like any other business. Our strengths are AI powered, because our project is AI powered, scalable, and fast interpretation, which you don't find anywhere else, which is the communication gaps effectively, potential for partnerships and accessibility. Then and accessibility organizations. Weaknesses, of course, are accuracy challenges in real-time interpretation. We know this. Hardware dependence for precise detection. Since hardware also comes with its own challenges, requires high-quality data set for multiple sign languages. Since right now we only use the Ugandan sign language, and the Asians or the other countries may not be helped. Threats: competition from big tech companies, high development and maintenance costs, and then the data privacy and challenges. Opportunities are many. We have a growing demand for AI accessibility solutions, integration with AR and VR smart devices, then the government and corporate adoption for inclusivity. Thank you so much. That's all I had.
Hello and welcome back to my YouTube channel. My name is Simon Arao, and in this video I'm going to be taking you through live demo of the sign language translator. In this case, our sign language translator has two options. The first option is using the upload video, and the second one is using a webcam. In this case, we're going to be using uploading the video. As you can already see, I've uploaded the video and then not waste time. So when I hit this translate the uploaded video button, it basically just passes this video to the backend, and the frames are extracted from the video, and these frames are passed to the model. But before that, they are pre-processed with the model processing. Then after the model has predicted the classes, as you can see here, comes to conclusion that final translation is good. And as you can see here, the most common class is 24, and the rest are 13, which has 2, then 31 is only 1. And in this case, the final translation is passed back to the front end. You can see. Thank you. Without further ado, we'll go to the lessons learned and the challenges. Basically, the key challenges that we experienced was the data scarcity. The Ugandan sign language datasets that was overfitting as we are training the models because of the limited number of videos that were in these datasets. It overfitting, and if we could get more funding in the near future so that we can scale up these datasets to increase the number of videos so that we can overcome the overfitting challenge. And also, data augmentation itself cannot basically overcome this data scarcity situation. So, and another problem was complexity movements of these sign language gestures that involve hand movements, and these are very hard to track as you're training your models. But as you can see, use the fine-tuning strategies to also overcome the overfitting and complexity of the movements. One of the key feature works that we intend to implement is the offline mode. This basically helps people that are in remote areas to easily access this sign language translator without needing an internet connection, which could also be costly in some areas. And also another key feature work here would be multi-platform availability. Launching this app as a mobile app or a web app, this could help in reachability and availability to very many people, in this case being widespread the masses. Then in conclusion, what were our key achievements? In this case, real-time sign language translation, basically using computer vision, a CNN model in this case. And this CNN model, based on the accuracy of that ranges from about 87% to 93%. And also, yeah, it was built for a low resource setting for the Ugandan context in this case.